Okay, this first one up here, you have a soluble ionic compound. What happens when it hits water? It breaks it apart?
Does it break the compound apart, or does it specifically break each individual molecule?
It breaks the compound apart, not the molecules away from each other. It breaks the molecule in half, or into its constituent ion pieces. So the cations and the anions separate out from each other. So if you've got something like CuCl2, a Cu goes one direction and two Cl's go another direction. The whole thing busts apart. Why is this happening?
Water has positive and negative charges.
Okay. Water's polar and has the ability to attack both the cation and the anion. Okay, somebody give me an ionic compound that's soluble.
CuCl.
Perfect. Okay, how about another one that doesn't have copper or chloride in it?
Sodium nitrate.
Perfect. Something else?
Potassium phosphate.
So why is the first one we wrote down, the copper 2 chloride, why is that one soluble? Because of the chloride. There isn't a copper rule, and the chloride rule says they're soluble, so it's soluble. Why is the second one soluble? Why is the sodium nitrate soluble? Sodium's a group 1A metal, and nitrates are soluble. So this compound is very soluble. And why is the potassium phosphate soluble? Potassium's first column, group 1 metal, so it's soluble regardless of what it's connected to. Okay, give me 3 that are insoluble.
Just a question.
Yeah.
Phosphates aren't soluble by themselves, right?
Phosphates are a PO4 minus 3. They can't be by themselves. They have to come with something. They have to have a cation to cancel out that negative 3, whether in this case it's 3 potassiums or 3 sodiums, or something like aluminum that's got a +3 charge on it. It's got to have, you can't just take phosphates and throw them into water. You can't just get phosphates.
But if it was something that didn't have a rule to it, it wouldn't be soluble.
Yeah, so if this was with the copper, we didn't have a rule for the copper, right? So this would be insoluble because phosphate's on that list. In that list, it is in the rule that's insoluble. Okay, somebody that's insoluble? That's not one of those 4, 6 ions?
Lead chromate.
They're both metals. Say again?
Lead 2 chromate.
Lead to chromate. Okay. Lead 2 chromate? Why is this one insoluble?
That's not soluble.
Because the lead's not soluble and there's no chromate rule, so this guy's insoluble for sure. Okay. Another one? Zinc oxide? Sure. You might know this is insoluble because it's the really, really white sunscreen stuff. Maybe lifeguards or somebody who's in the water a lot will put, sometimes you'll see kiters out on the water who are out there for like 8 hours. They'll come in and their face will be white. It's because they coated it with not just regular sunscreen, but zinc oxide sunscreen, which does a really good job of deflecting. Although, I did just read something about all of that being bogus. That all the sunscreens that we use in the United States, none of them stop cancer. But they do stop burning, but they don't stop the cancer. We can't really talk about that right now, though. Another one?
Barium sulfate.
Say again?
Barium sulfate.
Sure, barium sulfate. So there's a sulfate rule, and it says it's soluble, but the exception to that rule is if it's with the barium or calcium, or one of the three metals that's above it on the list. So, okay. All right. We want to balance these next ones, add states, and circle the ones that are ionic. So let's go ahead and do this first one. What are we going to do to balance this first one?
12 for the carbon.
A 12 right there, and 11 for the water. Okay. What do you want to do for states? What is this thing here?
A gas. Solid?
But what is it?
Crush.
Yeah, it's twice as big as glucose. It's probably sucrose. It could be lactose, but it's definitely a disaccharide. It's definitely two carbohydrates stuck together. I mean, I guess it could be maltose, could be double glucose, but it's definitely a solid. And the carbon? And the water?
Liquid.
Sure, I'm okay with that. Anybody in there ionic? Nope, no ionic compounds. Okay, next one.
CO2.
2 in front of the CO2. Okay, so our carbons are balanced. Now what?
Three
3 to
to the H2O.
the water, and now my hydrogens are balanced. On the right-hand side, that product side, I've got 4 and 3, so I've got 7 total. And then what do I do to my reactant side? If I put 3 O2s, then there's 6 oxygens here plus the one that's on this guy over here, and so then I balance it out with 7s. Okay, state.
Is that another sugar?
Nope, it's not another sugar. Sugars will have 5 carbons in them with hydrogens and oxygens, but usually 6 or 12.
Gas.
That's a very good guess, and I would say it's a gas, except the only 2 configurations that you can have for this molecule make it liquids. So the way that you know, or I'm hoping that you guys remember that this kind of compound is a liquid, is I know we said 1 carbon, 2 carbon, 3 carbons is gas, but that's only when it's just carbons and hydrogens. Now I've got an oxygen present. That changes everything. So if it's got a carbon, a hydrogen, and an oxygen in it, it's automatically going to be at least a liquid. Even the smallest one, which is basically a methane with an oxygen on it, that's a liquid at room temperature. That's methanol. So this guy's a liquid because he's tiny and he's got an oxygen on him.
So if it's bigger, like the one above it, it's solid.
Correct. Yep. And then gas, and then a gas, and then a liquid. What do we have? Anybody here ionic?
No.
Mm-mm. No metals, no ions. Okay, next one. What are we doing for balancing?
Add a 2 to the NH4CO.
Okay. That balances out our nitrogens and our hydrogens. Anything else? That's it? Okay. States? This is tricky.
Barium chloride is a solid.
If it was dry, it would be a solid.
Sorry.
So let's think about this for a second. If this was dry, this is barium chloride. What kind of compound is this? Okay, so what does this look like if you were holding it in your hand? What kind of solid? Powder? It would look like table salt, kind of look table salt, chunky table salt. So then what about the next one? The ammonium carbonate. What kind of compound is it? Ionic. How do you know it's ionic? That's two polyatomic ions, right? Ammonium's a polyatomic ion, so is the carbonate. So that's definitely an ionic compound. So what does this look like? Salt. So if I wanted to react the barium chloride and the ammonium carbonate together to get those two products, the ammonium chloride and the barium carbonate, would it make sense for me to take two solid salts and dump them into a beaker together? It wouldn't. It would be a lot easier if I could put them in as aqueous environments. And then they would dissolve, separate out. Because if I put these two things together, nothing's going to happen. Why not? If they're solids. Say again?
They're stable.
Yeah, they're stable salts. There's no reason for them to let go. Only the water molecule gets in and breaks them apart, and then they'll go find the precipitate. But these as solids will not react with each other.
So you don't have to have, like, when the H2O molecules break apart, they don't then bond with
The water molecules don't break apart.
No, they break apart.
Oh, when they break apart the salts,
Yeah.
yeah.
Don't, I thought that they kind of bonded with whichever was the positive or the negative.
They're like acquaintances. They like hang out for a little while, and then when they leave, they're gone. There's no actual chemical bonding going on. There's no new substance. And you guys did this in the last, was it the last lab? Where you took the salt and you tested the salt dry, you dissolved it, and then you boiled the water off, and then you tested the salt dry again. What were your results before and after the dissolving? Same. So did dissolving do anything? No. So no actual chemical reaction occurs. It's NaCl on both sides of that. And so you wouldn't have any issues with the water doing anything to either of these salts. So I know there's no water present, but what I want you to do when you see this is see two ionic compounds in your head, solid, solid. How often do you ever have a chemical reaction happen between two solids? Never. I mean, kitchen, do you ever put two solids together and get a reaction happening? I want to make oatmeal. Do I have ice and oatmeal? Is that going to work out? Not until the ice liquefies, right? So these things will not be able to react together unless somehow they get broken apart. And the only way these guys can get broken apart is if there's water present. So why isn't it written? Because you guys are chemistry students, you're supposed to know that kind of stuff. That's why. So, so this one is aqueous. Why? But why is it aqueous? Why isn't it still a solid even when it's wet? Chloride. The chloride says there's no barium rule having to do with chlorides. There is a chloride rule that says chlorides are soluble. So when this goes into water, it dissolves. Why is this side over here? Why is this one aqueous? The ammonium's aqueous no matter what, even though the carbonate rule says I don't want to be soluble. So now I jump over to the other side. What's the state for the barium carbonate? Yeah, there's no barium rule associated with carbonate, and the carbonate rule says I'm a solid. So this one's a solid. So what would we classify the barium carbonate as in this reaction? The precipitate. Okay. And then what do I do with this ammonium chloride? Still aqueous. So what are the spectator ions in this reaction? The ammonium ion and the chloride ions didn't do anything. They were aqueous on both sides. Okay, so then what do I circle? All these guys, right? They're all ionic compounds. All right, what am I doing next? Balancing out this next one? A 2 in front of the H2O. Yep, there are 4 and 4. Okay. Anything else? 1, 2, 3, 4. 1, 2, 3, 4. 1, 1. Oh, all right. That's easy. States?
Solid for the first.
For the same reason that we had the last one be aqueous and aqueous. Because otherwise, you're right, they would both be solids and then they wouldn't be able to react with each other. And a liquid for the water, and then what do we have here? It's aqueous, you are correct.
So water's just formed in that?
Yep.
Just more water?
This is an acid-base reaction, and the result of an acid-base reaction is a salt, which the sodium aluminite is, and water. Salt and water is what you get when you mix acids and bases together. So what am I circling with this one? What is that Al2? It's one of the like million polyatomic ions that I didn't have you guys know. Because that list might seem long and daunting to you, but it's a drop in the bucket of polyatomic ion possibilities. I'm not changing that list. I'm not adding this to it. It was just on the list. It was just on this. Okay. Next.
The 2 in front of the NaCl.
I don't think so.
6.
So, a quick, or how about a little, a shortcut that can help you get these things done a little bit more quickly. So on the left-hand side, you see a phosphate, correct? And on the right-hand side, you see a phosphate, correct? How many phosphates are over there on the right? So if you throw a 2 up here, that might help make everything come together. So when I put that 2 in front of that sodium phosphate, I balanced out my oxygens and my phosphates in one swap because the polyatomic ion did not change form. So now that I've done that, I know I've got 6 sodiums on that left side, so I'm going to definitely need to put a 6 right here. And so then what that does for me is gives me 6 chlorides on the right, which means I need to put a 3 in front of my iron 2 chloride. And then, and you're done, right? That fixed everything. So when you use sometimes you just get something to finish out balancing out because it has to. Eventually it's going to have to balance out. So you're going to write a number down and go to balance out the last piece and it's, oh, it's already done. So states? Yep, aqueous. Yep, aqueous. Solid and aqueous. Why is the iron 2 phosphate a solid? The phosphate rule says phosphates are solid and we don't have an iron rule, so the phosphate rule wins. All right, and then ionic. And the last one here, what do we want to do? What if I put a 2 right there and my iodides balance out? And then I can put, oh no, I see why you're, okay, let me back that up. So you have a 4 here, so you can balance out the oxygens? Okay, and then my sulfur's good. So I have 2 here, so do I need an 8 here? And so then I need a 4 there. Is that it? 2, 8 is 10. 2, 8 is 10. 4 and 4. 1 and 1. 8 and 8. Okay, cool. All right. What are we gonna do for our states? How do you think you would get yourself some sulfuric acid? I go get a container that had some sulfuric acid in it, but you can't get them 100%. They only come as dissolved in water. Acids only come dissolved in water or as a gas. And so I wouldn't want to be messing around with gaseous sulfuric acid and gaseous hydroiodic acid. So they'd probably just both be aqueous, and I'd mix them together. And then what about this guy here? Yeah. A terribly smelling, painful gas. Liquid. How about the iodide? Yep. It's a solid. Ionic compounds? No.
No.
Just the one with the polyatomic ion in it. Any questions?